Alrighty, hey guys, and welcome back to another kind of mini lesson. This one is going to be going over the idea of impulse and how we can kind of see that in car safety and what is known as the crumple zone. So here's our situation. We have two different cars that are going into a crash test. Um, the first car, car A, has a crumple zone of 1/4 of a meter, so 0.25 meters, and the second car has a crumple zone of a full meter. Um, in this crash test, both cars are going to be driving in a wall at 65 miles per hour, which is approximately 29 meters per second. What we want to know is what is the average force of the seatbelt on the crash dummy? And we're going to make the assumption here that our crash dummy is 80 kilograms. So, as I already told you, this is going to kind of be an impulse one. The reason why I know this, that this would be an impulse problem, is because it's asking for the average force during a collision. So whenever we see something about the force during a collision, we know that we're going to be dealing with impulse. So when you start thinking about what things do we know about impulse? Well, over here, we know that impulse, and yes, sometimes you see it represented as an I, sometimes you see it represented as a J, just kind of depends on who's doing the literature. And so here we're going to be talking about impulse and the fact that we know that it is the change in momentum. The change of momentum of whatever the object is. And so typically that's going to be mass times the change in velocity. The other definition that we have here is that impulse is equal to the integral of force dt from your first time to your second time. Well, here this is just talking about the actual force itself, and we know that a collision force typically looks something like this. It's a really big spike. Actually, typically it's skinnier than that. And here we're asking for the average force. We don't want to know what the force was at the beginning or the middle. We want the overall, the average force on the dummy. And so there is a way that we can use calculus to help us get there. We use what's known as the mean value theorem. The mean value theorem is actually going to be talking about the force. It says the force average is 1 over the change in time, T1, T2, times the force dt. And that's pretty much just saying that anywhere in this integral, there's going to be this average force. It kind of just makes this work. Physics teacher, not a calculus teacher, but this is the mean value theorem. The really cool thing is if we start to kind of rearrange this, we go ahead and bring the delta t up. We get this. Hopefully you guys are noticing that this is the same thing here, which we know is then equal to j. So this is another definition of impulse. Not only does it have to be the integral here, we can also say, due to the mean value theorem, that it's actually the force average times the time of the collision. And so we can put that here with our original definitions. So these are the things that we're going to be looking at. We want to solve for the force average, and since this is what we're solving for, that means somewhere during this process, we need to know what was the change in momentum and what was the time. Oops, sorry, I meant to change colors there. How long the collision took. So we can go ahead and start solving for these things. Let's start with the change in momentum, and we're going to start with that because it's the same for both cars. Both cars have the dummies here, both the dummies have a mass of 80 kilograms, an initial velocity of 29 meters per second, and a final velocity of 0 meters per second. And this is because we're talking about the actual collision itself. So once it hits to 0, after that it would bounce off the wall, and that would no longer really be part of the collision itself. That's when we could use conservation of momentum to see, what was its rebound speed. But here we're talking about the actual collision itself as it hits the wall. And so we're talking until that stopping point when it has that 0 meters per second. So we can go ahead and solve this. The change in momentum is your final momentum minus your initial momentum. So we're going to do the mass times the velocity final minus the mass times the velocity initial. And so we're going to have 80 times 0 minus 80 times 29. And we end up getting, let me just double check here and make sure, negative 2320 Newton times seconds. And so here the negative is really, saying that we're going from a ton of momentum to no momentum, or less momentum. And so that's just saying that the object lost momentum. So both cars share this because these quantities were true for each of them. The next thing then that we need to talk about then is trying to find our change in time. And this one is going to be different. We're thinking about change in time. If we're thinking about this typically means we're going to go back to our kinematics. So for car A, we know that the delta X is that crumple zone, which is 0.25 meters. And for car B, the crumple zone is a little bit larger at 1 meter. So I think back to my kinematics. I'm like, okay, what equations have delta X in it? And I know that delta X equals V naught T plus 1/2 AT squared. And I know that V final squared equals V initial squared plus 2A delta X. The problem here is that both of these have A in them. And we don't necessarily know the value of the acceleration during this time. And it's going to be a little bit too complex to try and figure that out. And so we've kind of hit what seems to be a stump. But it's not actually a stump. If you think back to it, we're using the force average. Because we're using the average force, that means we're just using one number. And because it's one number, we can just think back to mass times acceleration. And we know that acceleration then would have to be constant. And so yes, we know that obviously the force is varying, then there's a varying acceleration. But here, because we're using the average force, we can go ahead and say, hey, acceleration is going to be constant here. We can kind of make that assumption to make this work. Because of that, we can then go ahead and say, okay, if A is constant, we can use this formula. We couldn't use this formula to start with. We couldn't just say delta X equals V delta T, which so many students like to do. This is a no-no. And this one only works if you know that you have a constant acceleration. A constant velocity. But we have a velocity of 0 and 29 and everything in between, so that doesn't work. However, when we say that we have that constant acceleration, we can now use this new formula. So because we can use this new formula, we're ready to go, except for the fact that we got to figure out what V average is. So here we're going to use the formula that V average is 1/2 V initial plus V final. So that's how we're going to find our average velocity here. So V average is equal to 1/2 0 plus 29. I did this backwards. Addition does not matter. So that gives me 14.5. Now we're ready to go ahead and solve. So I'm going to come up here and say, okay, delta X equals our V average delta T. So 0.25 equals 14.5 delta T. My change in time for the first crumple zone, 0.25 divided by 14.5, gives us a nice 0.01724. I'm going to highlight that in blue so I can come back to it in a minute. And we can do it for the other car. And here we get a delta T of 0.06897. And once again, I'm going to highlight that in blue so we can come back to it. So now if we go back to our original equation, we were trying to find our force average. We needed to know our change in momentum and our change in time. I did not highlight it, so I'm going to now. We have our change in momentums, we have our change in time, so we're ready to go. So once again, our change in momentum was 2320 newtons per second. Our delta T for car A was 0.01724 seconds. Our delta T for car B was 0.06897 seconds. So let's look at car A then. So for car A, we're going to say our change in momentum is equal to our force average times our change in time. We can plug these numbers in. zoomed out a little too far there, so 0.01724. We go ahead and do our division here, and we're going to get a really large number. 0.01724. Make sure you get those numbers right. And if you're being really precise, you could actually just carry that from your calculator. So that's what I'm going to do here, is just carry this number inside of my calculator. So that's just a really good reminder of using what you have at your access. And when I do this, I get that my force average is this. So 134,000 newtons, 134,000 newtons. If I come over here and I do this same thing for car B now, so once again, the change in momentum is equal to that force average times the time of the collision. And so the 2320 is equal to that force average here. Our time is going to be, it was a little bit longer time. Still less than a second, but a little bit longer. So if I do this again, we get that our force average is equal to 33,640 newtons. So notice here, just by changing the crumple zone, we're able to significantly reduce the average force that the dummy, or actually whoever's going to be sitting in the driver's seat, is going to feel. Obviously, hitting a wall at 65 miles per hour is catastrophic. We wouldn't want to ever hit something going that fast. Most people, obviously, if they can, slam on their brakes before hitting into a collision. And so that initial speed's a lot smaller, that change in momentum's a lot smaller. So even if the time of the impact is still pretty quick, that change in momentum is a lot smaller, so these numbers are going to be smaller. But we can see the other things that the car companies control. They can't control how quickly your reflexes are. Are you going to brake? Did you see it or not? But they can do their car safety. And so this is one of the things that has been changed. And once again, one of the big things I wanted to note was this idea over here. Because we're talking about the force average, we can use that idea that it's a constant acceleration, allowing us to use some of these formulas with a velocity average, which we don't typically use. And once again, that's because we're talking about the force average of the collision.